transistor, right? It is a transfer resistor. Why I keep emphasizing the transfer aspect? That is because it has 3 terminals. It is so special because we use a third terminal, which is called the gate, to control, you can say, the resistance or the current or whatever, or conductance, whatever you want to call it, the resistance, conductance, current at the other 2 terminals. So it's as simple as the switch on the wall, right? In the future, we might not have switch anymore because technology advanced so much. But now you see that I turn on, off the switch easily, right? I just maybe even a baby can turn it on and off. But I can control, I can make all the lights in this room on and off. That is the important thing about the transistor, right? A very tiny signal, I can control all the lights, which if I touch them, I will get electric shock because of the high power, right? So this is the important concept. And you see that I change the voltage or control the switch at the gate, but the current does not change at the gates. It changes at the source and drain. That's why it's called transfer, right? This is very important because later I will keep asking, what is transconductance? This concept is important. You want to know that I add something to the gate, how much I'm changing the drain current or drain output impedance, whatever, right? So on the left, that is what I said. Usually what we model in a digital circuit as a 0 and 1, we just say it's completely on or completely off. On the right, we just draw the whole symbol, but basically we care really about how the current or how the resistance conductance changes along source and drain when I modify the gate voltage. Okay, remember this transfer concept. Another thing we want to be very careful is to really understand or label the source and drain correctly. Because if you don't do it right, you will not be able to map to the right circuit. And then you will use the wrong equation. Okay, so now you may feel that what I'm saying is meaningless, but this is going to be at least in some quiz or test, right? I want to make sure that you know how to figure out where is the source and drain. This one shows the 3D structure of a transistor. We have the gate, we have the source, we have the drain. Because this is N, and this body is P, so this is a NMOS, correct? This is an N-type transistor. When we say it is NMOS, because when the VG is larger than the threshold voltage, we are going to induce some electron here. The conduction depends on the N-type carrier, which is negative. N stands for negative, right? To do the conduction, right? So this is an NMOS. This is the cross-section of the NMOS. What we are doing is just look at the 2D instead of the 3D, right? So we just look at here. This is source, this is drain, right? And this is the symbol. Okay. But however, how do we define what is a source, what is a drain? This is very important. Let's start with NMOS. What is the symbol of an NMOS? This is the symbol, right? Based on this, what is the gate? It is easy, gate. Gate must be this one, right? It's the one that is insulating from the rest of the part, but it's going to control the other part. Which one is the source? Which one is the drain? Very often we say, wow, this arrow is the source. Most of the time it's correct, but this is just a symbol we draw on that. A more rigorous way of determining which one is the source will depend on the potential. For example, if this is at the lowest potential, the current is going to go from highest potential to the lower potential, right? You need to memorize this. Currents always go from higher potential to lower potential, just like the ball roll from the top of the hill, right? But however, where does the electron go? Electron is going to go from the negative terminal to the positive terminal. Okay? Remember, of course, right? Electron is repelled by the negative terminal to the positive terminal. But the current is still going from the positive to the negative by definition. Negative charge flowing from left to right, we will say that I have a positive current going from right to left. This one, yeah.
Source a little bit more than the drain. If you were to, say, invert the voltage to a -3, would you destroy the transistor, or would it still just flow, but it would maybe flow at a proper rate?
Okay, so I will answer your question later, right? So he's saying that the doping of the source drain might not be the same, but in this case, but they are still the same type, right? Still N, yeah. I would answer that later, right? Then what happened? Like, let me still assume source and drain have the same type of doping, okay? So now what I want you to follow is that, do you agree that the electron goes from the negative potential to the positive potential? Okay. What is the carrier of the NMOS? The current carrier. Electron, right? It is the electron causing the current, right? It's just like I ask you, what is the carrier of the water flow? You would say water molecule. What is the carrier of, let's say I have alcohol river? Then it will be the alcohol molecule, right? The carrier of the NMOS is electron, right? Because I just told you that is how it operates. We will discuss more later, but you agree with me from E128 is electron, right? So the electron goes from the negative terminal to the positive terminal. That's why the negative terminal is the source and the positive terminal is the drain. Just like the sink in your kitchen, the source is the tap, right? The water comes from the tap and it is the molecule that is the carrier. It comes from the source and then go to the drain of your sink. You turn the knob, that is the gate. Okay? So remember, we don't define the source and drain based on how you draw it. We define based on the potential of the terminal. This terminal has a lower potential. So this is the source and this is the drain because the electron comes from the negative terminal, right? Now go back to your question. You say that what if they have different amount of concentration? We still use the same definition because we still need to decide which one where the electron comes from. Since it comes from a lower potential, so it is the source, regardless of their doping. Of course, you still need to have N-type. Once you change the type, then there is a different story. Good question, right? So how about the PMOS? So we usually draw in this way. And of course, usually we will say the one with the arrow is the source. But let's think about what we are doing. If this is VDD, the currents go from the top to the bottom, right? Current always go from higher potential to lower potential, whether you're NMOS or a PMOS or whatever, because currents means the positive charge, right? PMOS has the carrier, has hole as its carrier, okay? So where does the hole come from? Higher potential, right? Because hole is positive, okay? So as a result, the negative terminal is the drain, but the positive terminal is the source. Okay, so in this particular case, this is source and this is drain. Right? And this aligns with what you have been thinking about because we always make this arrow associate with the source. So I draw it correctly. But usually the drawing is okay, but we need to be careful. We need to make sure that the source, make sure which terminal has higher potential in order to determine where is the source and where is the drain. This is important later when we map to different topology of circuits and also use the equation. Okay, is that clear? Right, I spend so much time on something looks very simple because I want to correct the concept. This is very important. Okay, so what is the role of the gates? As I said before, right? It control the resistance or conductance or whatever between the source and drain. Right, so this is, if you forget everything about EE 128, you should have this concept. I give you a transistor, you know that, well, this is just a resistor. I control the gates, I'm going to change its resistance. Okay, that's a fundamental concept. So let me test you, see if you understand what I said. I have 4 circuits on the top left. Which one is the, of course, I don't need to spend time on this. I know these are all the gates, right? On the top left, which one is source, which one is drain? Okay, let me start. This one, first I need to identify if it is an NMOS or a PMOS. Because the arrow pointing in this direction, I know it is NMOS, right? You will know whether it's NMOS or PMOS based on different information. Maybe it is given, or maybe you are the circuit designer, you know that. So I know this is NMOS. So I know I compare these two terminals. I see that this one is a higher potential. This is 1 and this is 0. And then I know that electron comes from the lower potential to higher potential, right? So this is the source of electron and this is the drain. Okay, this is a little bit counterintuitive because we have been thinking of looking at this symbol. Now, why we want to make something so troublesome? Why I did not draw in another way? Because in your circuit operation, particular analog circuit, or like the switch logic, what do you call? The transmission gate. The two terminals might have different potential throughout their lifetime because you apply different voltage, right? When you analyze it, you keep thinking this is source, you will keep using the wrong equation. Okay, so this is source and drain. So how about you help me to do this, anyone? On the left and right, which one is source? How about just say, for the left one, is it source or drain? Drain, because higher potential, very good. How about this one, the left and right? Which one is source, which one is drain? Someone say we don't know or we don't care now, right? Because they have the same potential, it doesn't matter how I substitute the equation, it won't mess up, right? I call drain source, source drain, they still have the same value, right? So you can call it source or drain, doesn't matter, but then the other one, you want to call it drain or source, okay? How about the last one? What is the terminal on the left? Source, because it's lower potential, and because it's NMOS, right? If it is PMOS, it will be opposite, okay? So this should be very simple, but don't make mistake on this simple thing, okay? Good. So we talked about the cross-section of a transistor before, right? And here just an example of a 90 nanometer technology. We just want to appreciate the scale. For example, in 90 nanometer node, we have the gate length of 90 nanometer, right? It's a good time to review this unit. In terms of meter, for example, you know 1 millimeter equals to 10 to the power negative 3 meter, right? 1,000 millimeter is 1 meter. That is easy. How about 1 micrometer? Another, yeah, good. Another 1,000 times, right? Minus 6. How about 1 nanometer? Exactly, yeah. I know you know that, but just review. Another 1,000 times, right? That's nanometer technology. And we also have this angstrom unit, right? This is not SI, but this is, do you remember what it is? Thank you, 10 to the negative 10, right? It means 10 angstrom equal to 1 nanometer, right? The distance between two silicon is in the order about 0.5 angstrom. So you see that when we talk about nanotechnology, you are really close to countable number of atoms, which is very amazing. It's not amazing to have countable number of atoms. It's amazing that you can form on a 300 millimeter wafer with all this countable amount of atom device uniformly, and they all work well. Okay, they all work well. Okay. Anyway, so you see the gate length. I mean the oxide thickness, right? Just remember between the gate and the substrate, there should be an oxide, and this oxide is about 18 angstrom, which is 1.8 nanometer. Okay, and this gate length is 90 nanometer, right? So just as an example. Okay. And for the gates, we use something called polysilicon. It is just silicon, but they are not crystalline, they are polycrystalline, and they're very conductive. But however, when we come to the so-called FinFET, for example, in this case, right, it's no longer state of the art, right? We have even more advanced nanowire, but we become something called 3D transistor. So let's take a look what it looked like. Instead of have this so-called planar structure, right? This is planar, and you expect the electron will flow on the surface from the left to right, right? Electron from left to right, but current from right to left, right? If this is source and this is drain. We actually have a fin. This is the fin. And this is source, this is drain. And this is the gate. Now, what is a transistor? Just like the water pipe analogy, it's just like a water pipe. And then you use your hands to squeeze it, to pinch it off, so that you turn on and turn off the current. Now, in a planar transistor, it's just like you only have one finger to pinch off it in one direction. Now, imagine if the pipe is very wide and your finger is very narrow, it will be difficult to pinch off the current, right? If I have 4 fingers pinching from the top, it will be easier, because when the gate length is much longer, it will have a better control. It won't be leaky. But when we scale the transistor, we make it smaller and smaller, become 20 nanometer, about or 40 nanometer length, it will be too short, just like I only have a 1 finger, right, to pinch it off. So how can we increase the controllability? Very good. He said, you wrap it. You use 2 fingers, one on top and one on bottom. Push it from top and bottom, right? Isn't that it's easier to pinch off something, right? One from top and one from bottom. And that is called FinFET. So you see that this is a metal gate. What it does is, here, the red one is still the oxide, insulating. And then we wrap it with the metal gate, with a conductor, which is the gate, so that it can control it electrostatically. They are not really pinching like what we're doing with the water pipe, right? They are just use the electrostatic force to turn on and turn off the current. And that's why we have the so-called 3D transistor. And this is called FinFET. Is that okay? And now we talk about nanowire also. What is nanowire? It's not a fin, it's just a wire, really a long wire. And then we wrap it in all directions with the metal. And you can imagine, it's just like I use my hand in this circle shape and pinch off the pipe, right? It's much, much easier, right? So a few questions to you, right? Why do we use metal gate? Just now I say that we use this polysilicon gate. I think you can imagine, because metal gate has a higher conductivity, right? So it is going to reduce the RC delay. Because for the gate, in order to turn on the transistor, you need to apply a gate pulse. It has a delay. You think it's very fast, but yeah, it's very fast, but we are at very high speed, right? In nanosecond or in picosecond already. So a little bit resistor is going to reduce it by 2 times or whatever. That reduce the speed. Another is the so-called reduce the gate poly depletion. I just write here for your information. I won't explain it. Reduce gate depletion. This is going to increase the effective oxide thickness. You don't need to understand this. Another thing you see here is that we are using something called high K dielectric. What does it mean? This is good to understand. Again, in our transistor, we have an insulator, right? Like this one. We usually use oxide, right? Usually the traditional one is silicon dioxide. So it has a permittivity equals to 3.9. So the capacitance equals to the permittivity divided by thickness of the insulator. You all learned that before. Later you will see that, as we said, the transistor is that we want to control the current or conductance in the channel. So we want to have a large capacitance. The larger capacitance can induce more electrons, so you reduce the resistance. But if we want to increase the current, then it means I need to keep reducing the thickness of the device, right? When you make it really thin, then you run to a problem called tunneling, quantum tunneling. Probably you heard about that. If there's a wall, right? I run to the wall, of course I cannot go through unless I have enough energy to go through, right? But when the wall is very thin for electron, quantum mechanically, they can go through. And then you cannot stop the current going from the gate to the substrate. And then you have a lot of leakage. That's called tunneling. So we cannot keep reducing T. So what can we do to increase the capacitor? Increase the epsilon, the permittivity, right? So for example, we can use hafnium dioxide, which is very commonly used and its derivative are used very often. It has a wide range, but maybe we can say like about 30, okay? Then it means that for the same thickness, I can increase the capacitance for the same thickness. Okay, so that can avoid the tunneling while at the same time I have enough capacitance to induce a lot of electrons. And actually this is related to the control also. Okay. We don't, because this is an insulator. Now, but then when you say doping, do we dope the insulator? Actually, they do something to that just for quality. So the doping is not to increase the conductivity. This is a very complicated process. Right? It can be like highly confidential in TSMC or whatever. So they may do some doping, or the doping can come from different treatment or whatever, not necessarily implantation. Yeah. And definitely we need the FinFET for analog, right? I started this slide 4 years ago. At that time, I even say that maybe no need, but now you need it. Just everything is analog. It's FinFET now. Okay, but we still study the basics. So for all of you, right, when you start working in the industry, maybe you will be using the FinFET to design the circuit. That definitely for digital, analog maybe also. But the concept is the same, right? We are talking about analog circuits, so we don't need you to understand the device physics, but how you turn on, turn off, and all the trade-off are still similar. GMR out. Okay, so